Hello guys, welcome to the channel. My name is Shakir and I am the MD of IT from Silver India. I will continue with the fundamentals of software architecture. To review, the software architecture of the system is the set of structures needed to reason about the system. By reason, we refer the ability of the stakeholders to understand, analyze, make decisions about the various aspects of the system, such as its functionality, performance, scalability, reliability, maintainability, and security. They can help identify potential issues and trade-offs, make informed decisions, and communicate effectively with other stakeholders. These structures comprises of software elements, relation among them, and properties of both. There are four categories of structures: component and connector structures. This shows the system as a set of elements that have runtime behavior, which are components, and interactions, which are connectors. Module structures show the system as a set of code or data units that have to be constructed or purchased. Allocation structure shows how elements from module and component connector structures relate to the non-software structures such as CPUs, networks, and development teams. Behavior structure describes the behavior which is dynamic in nature of the system, including the sequence of actions, events, and interactions between various components and external systems. Behavior structures provide a view of how the system behaves and interacts with its environment. Structures represents the primary engineering leverage point of an architecture. In engineering, a leverage point is a place where a small change can have a big effect. By focusing on the structures within the architecture, engineers can identify key areas where a small change can have a big impact on the overall system. For example, if you are building at home, the placement of load-bearing walls and the arrangement of beams and columns can greatly affect the strength and stability of the building. Similarly, in software engineering, the way you structure the code have a major impact on its performance and scalability. Collectively, structures represent a powerful approach of creating the architecture. Now, functional requirements specify the expected behavior of the system in terms of what it should do and how it should perform certain tasks. These requirements are typically described in the form of use case, user stories, and functional specifications. To satisfy the functional requirements, the system design must include appropriate set of responsibilities that define how the system will perform those tasks. Responsibilities in software design refer to the tasks and functions that a module, component, or class is responsible for. Each responsibility is typically defined in terms of input, output, and behavior. By carefully designing and assessing responsibilities within the design, the software can be developed to meet the functional requirements. On the other hand, quality attribute requirements, they specify the non-functional aspects of the system such as performance, scalability, reliability, and security. Now, the design of the system architecture must take these into account. These quality attribute requirements should be there in the system to ensure that it meets the desired level of quality. Now, the structure and behavior of the software architecture plays a crucial role in satisfying the quality attribute requirement. For example, the architecture may include mechanisms for load balancing to ensure that the system can handle high volume of traffic, or it may incorporate security features such as encryption and access control to protect the sensitive data. In summary, to satisfy the functional requirements, the design must include appropriate set of responsibilities that define how the system will perform to the task. To satisfy the quality attribute requirement, the architecture must be designed with structures and behaviors that ensure that the system meets the desired level of quality. Now, let's understand the quality attributes. A quality attribute is a characteristic or property of a system that can be measured or tested to evaluate how well the system meets the needs of its stakeholders. Now, quality attributes are often used to assess how well a system performs just beyond the basic functions or features, and can be thought of as a measure of utility of a product along with some dimensions that are important for the stakeholders. Now, quality attributes can take many forms depending on the nature of the system and the need of the stakeholders. For example, quality attribute might include performance, that is speed or efficiency with which a system performs its task, or reliability, the ability of the system to perform consistently and without errors over time. Usability is how easy it is to use the system and operate the system. Security, again, is the ability of the system to protect the data and prevent unauthorized access or attacks. Scalability is the ability of system to handle increasing levels of demand or usage. And now maintainability is how easy it is to maintain and modify the system over time. Now, quality attributes are important because they allow the stakeholder to evaluate and compare the different systems based on their specific needs and priorities. By measuring and testing quality attributes, a stakeholder can gain a better understanding of how well a system will meet their needs and make informed decisions about which system to choose and how to improve an existing system. Let us focus on understanding the following. How to express the qualities we want our architecture to exhibit. and how to achieve the qualities through architectural means, and how to determine the design decisions we might make with request to these qualities. In fact, if functionality was the only thing that mattered, you wouldn't have to divide the system into pieces at all. A single monolithic blob that's like a big piece of code with no internal structures would be just fine. Instead, we design the system as a structured set of cooperating modules, elements, layers, classes, services, database threads, and so on and on, to make them understandable and to support the variety of other purposes. Now, the other purposes are the quality attributes. Functionality describes what the system does, and quality describes how well the system does those functions. That is, qualities are attributes of the system and function is the purpose of the system. There are two categories of quality attribute. The first category includes those attributes that describe some property of the system at runtime. That is, how it is with the availability and performance and usability part. And the second category includes those that describes the property of the development of the system, such as modifiability, testability, and deployability. Now, quality attributes can never be achieved in isolations. The achievement of one will have an effect on the other. So, sometimes positive and sometimes negative on achievement of the other. For example, almost every quality negatively affects performance. Think about it. Take portability, for example. The main technique of achieving portable software is to isolate the system dependencies, which introduces overhead of the system's execution, typically some process or procedure boundaries that hurts performance. Determining a design that may satisfy quality attribute requirement is partially a matter of making the appropriate trade-off. Non-functional requirement analysis. Now, it's a challenge of testing quality attributes as their definitions are not always clear and testable. It is not meaningful to say that the system is modifiable without specifying what type of change it can accommodate. Similarly, a system can be robust to a certain faults but may be affected by others, making it difficult to give a definitive statement about the quality attribute without considering the specific context and circumstances. Now, the challenge of categorizing particular issues such as denial of service attack, which is a special type of cyber attack where the attacker tries to overload the system or the network or the website with traffic or requests, making it unavailable or unusable for users. Now, the goal of the DOS attack is to disrupt or disable the targeted system rather than to steal some data or cause damage. Now, the quality attribute categories like availability, performance, security, usability can all claim ownership of this. The debate over categorization does not help the architects to understand and create effective architectural solutions. So the focus should be on finding solutions rather than debating the ownership of the issue. Every attribute community has created its own terminology. For example, when it comes to system operations, the performance community uses terms like events, the security community uses attacks, and the availability community uses faults, and the usability community uses user input, although they might all be referring to the same event in different languages. We use common form to specify all QA requirements as scenarios. Now, this addresses the vocabulary problem we identified previously. The common form is testable and clear. Thus, it provides regularity on how we treat all quality attribute scenarios. All quality attribute scenarios have 6 parts. Stimulus. We use the term stimulus to describe an event arriving at the system or a project. Now, stimulus can be an event to the performance community, or a user operation to the usability community, or an attack to the security community, and so forth. So these are terms used by all these communities. Thus, a stimulus for modifiability is maybe a request for modification of a feature. A stimulus for testability is like a completion of unit of development. A stimulus must have a source. It must come from somewhere, some entity, either human or computer generated. Now, the source of stimulus may affect how it is treated by the systems. Like a request from a trusted user will not undergo the same scrutiny as a request by an untrusted user. Response. The response is the activity that occurs as the result of arrival of the stimulus. Now, the response is something an architect undertakes to satisfy. It consists of responsibilities of the system or the developers, something that they should perform in response to the stimulus. For example, in performance scenario, an event arrives and the system should process that event and generate a response. In modifiability scenarios, a request for a change occurs and the developers should implement the modification, that is the change request, without side effects, and then test and deploy the modifications. When the response occurs, it should be measured in some fashion so that the scenario can be tested. That is, so that we can determine if the architect achieved it. For performance, this could be like the measure of latency. Latency means the time it takes for a single unit of data to travel from its source to the destination, and it receives a response or throughput, which is an amount of data that can be transmitted over a period of time. usually measured in bits per. For modifiability, it could be the labor time required to deploy the modification. The environment is a set of circumstances in which the scenario takes place. Often this refers to the runtime state. The system may be in overloaded condition or normal condition. The stimulus arrives at some target. Now, artifact may be a collection of system, either the whole or a piece of it, and failure or a change request may affect just a small portion of the system. A failure in the data store may be treated differently from the failure in the metadata store. Now, modification of the user interface have faster response time than modification of the middleware. Now, achieving quality attributes through architectural patterns and tactics. We now turn to tactics an architect can use to achieve the required quality attributes. A tactic is a design decision that influences the achievement of a quality attribute response. It directly affects the system's response to some stimulus. Tactics may impart portability in one design or high performance in another. Architectural pattern, they describe a particularly recurring design problem that arises from a specific design context and presents a well-proven architectural solution for the problem. Pattern typically have multiple design decisions. In fact, they may contain multiple quality attribute tactics. Consider the design problem. Separating concerns in a complex user interface. Now, the context is a web application or mobile apps. Now, architectural pattern we can use is the model view controller. Consider design problem where we want to decompose a complex system into more manageable components. The context could be any large scale enterprise application. Architectural pattern we may use here is the layered architecture. Consider the problem breaking down a monolithic application into loosely coupled independently deployable services. The context could be any large scale system involving business requirements and it requires some kind of scalability and resilience. The architectural pattern we'll use here is the microservices architecture. Consider the design problem where we want to integrate multiple systems and services into a unified application. The context could be again in an enterprise system and distributed system and system with heterogeneous components. Now, the architectural pattern here we may use is the SOA pattern, that is service oriented architecture, which is used to guide the overall architecture of the system. Patterns are often used to guide the overall architecture of a system, while tactic is used to make a specific decision that influence the achievement of a particular quality attribute response. Here are some tactics used to improve availability of a system. Replication. Now, this tactic involves creating multiple instances of the component or service and distributing incoming requests across them. If one instance fails, the request can be automatically redirected to the other instance, ensuring that the system remains available. This tactic will also improve performance by distributing the workload across different instances. Redundancy. This involves duplicating the components or services to help provide a backup in case of failure. Redundancy can also improve performance by allowing multiple components and services to handle requests in parallel. Load balancing. Here the load balancing involves distributing incoming requests across multiple instances of a component. And this is to ensure that no single instance is overloaded. This tactic improves availability by ensuring that the system can handle high volume of traffic without becoming overloaded. Now, failover. In failover, we involve automatically switching to the backup system or some component when the primary system or component fails. Now, this tactic can improve availability by reducing the downtime in case of failures. Disaster recovery, it involves creating backup of the system and system configurations to ensure that the system can be quickly restored in case of any failures such as natural disaster or any hardware failure. Now, this tactic can ensure that the system remains available even in the event of a major outage. So let's discuss the tactics that can ensure that the system remains available even if there is a major outage. Modifiability. So if you want to achieve modifiability, the tactic is abstractions, because now you can hide the implementation details behind an interface to reduce the coupling between the components. Example, in case of programming, you can use the abstract factory pattern that provides an interface for creating families of related or dependent objects without specifying the concrete classes. So if you want to achieve encapsulation, then the tactic you can use is you want to group related functionality together to make it easier to modify and maintain. In programming, you can use the singleton pattern to ensure that the classes has only one instance and provide a global point of access to it. It helps in achieving encapsulation by restricting the access to the instance and making it globally available. So if you want refactoring, then you should restructure the code to improve the modifiability without changing the functionality, and decorator pattern can help you achieve this because you can add additional responsibilities to the object dynamically, and it will help in achieving refactoring by allowing the modifications of the behavior without changing the original class. If you want quality attribute performance, then the tactic you should use is caching, because you can store the frequently accessed data in memory and reduce the time it takes to retrieve it from the database or the external system. If you want security, then the tactic you should think about is authentication, where you verify the identity of the user or system before granting access. Encryption, where you're protecting the sensitive data by encrypting it during transmission or storage. Or access control, where you're restricting the resources based on roles and permissions. If you want testability, then mocking is a good tactic to apply, where you can mock the components and services to test a component in isolation. And unit testing, of course, where you're writing automated tests for individual units of code to ensure that they behave correctly. The reality is that architecture often emerges and evolves as a result of many small decisions and business forces. For example, a system that was once tolerably modifiable may worsen over time through the actions of developers. That is, they keep adding features and they keep fixing bugs. Similarly, a system's performance and availability and security and other quality attributes, they degrade over time, again through well-intentioned actions of the programmers who are focused on their immediate task and not on preserving the architectural integrity. Now, this is called death by thousand cuts in software projects. The developers may make some poor decision due to lack of understanding of the structures of the system, or they have pressure to keep up with the schedule, or they have the lack of clarity in the architecture. Now, this deterioration is a form of technical debt known as architectural debt. To reverse this debt, we typically refactor. So a refactor may be done for many reasons. For example, you might refactor a system to improve its security, placing different modules into different subsystems based on the security properties. Or you might refactor a system to improve performance, basically removing all the bottlenecks and rewriting the slow portions of the code. A refactor to improve the system's modifiability. For example, when two modules are affected by the same kind of changes over and over because they are duplicates of each other, the common functionality could be factored into its own module, thereby improving cohesion and reducing the number of places that needs to be changed when the next change request arrives. So in summary, functional requirements are satisfied by including an appropriate set of responsibilities within the design, and quality attributes requirement are satisfied by the structures and behaviors of the architecture. Now, some questions for you to think about. Can you write the availability scenario for a software for a driverless car like Tesla, for example? The second question is, what tactics are used by a load balancer when it detects a failure in one of its instances? It is good questions to think about, and I hope this helps. Thank you.